Welcome back, and in this video we're going to be looking at using combustion data and also looking at PV equals nRT equations. So we're on page 8 of your notes and we're looking at this combustion data. Now we know that when we burn a hydrocarbon we produce carbon dioxide and water. Now all the carbon from the compound ends up in carbon dioxide and all the hydrogen ends up in the water. So for every 1 mole of carbon dioxide produced, my compound has got to contain 1 mole of carbon. And for every 1 mole of water produced, the compound must contain 2 moles of hydrogen. Now, oxygen we can't calculate in this wet method because the compound is being burnt in oxygen. So I don't know how much oxygen is coming from the compound and how much from the air is being burnt in. So let's have a look at an example of one of these questions. I've got a mass of a compound. My compound contains carbon, oxygen and hydrogen. And on combustion it gave a certain amount of carbon dioxide and a certain amount of water. So the first thing I'm going to do is I'm going to work out the moles of carbon dioxide. So that's mass, which is 3.52 divided by 44. And that will give me the number of moles of carbon dioxide. Now I know it's a 1-to-1 ratio between that and the carbon. So if this is the number of moles of carbon dioxide, it's also the number of moles of carbon. So to find the mass of carbon, I'm just going to times by the RMM or RAM, which is 12, and I get 0.96 of a gram. I could do the same thing for the water. I've got 1.44 grams of water divided by the RMM, which is 18. I know that for every 1 mole of water, I get 2 moles of hydrogen. So I'm going to times that by 2, which will give me the number of moles of hydrogen, and then times by 1, which is the RAM of hydrogen. And I get 0.16 of a gram. So I know now the mass of my carbon, and I know the mass of my hydrogen. I can use that and the mass of the compound total to find the mass of the oxygen. So that would be 2.40, take away 0.96 and 0.16. And that gives me 1.28. And that's the grams of oxygen. So now I'm going to use exactly the same method as I used before in the previous pack to find the empirical formula. I've got my masses, I can divide through by my RAM to give us the number of moles. So we've got 0.08, if I do that calculation there, 0.16, and again 0.08. So divide through by the smallest, and I get 1 to 1. So the ratio of the atoms is 1 to 2 to 1. So my empirical formula is CH2O. So I'm going to look at the next example on the top of page 9. This time I'm told I have a hydrocarbon. Now hydrocarbon contains carbon and hydrogen only, so I don't need to worry about water. So carbon, well the carbon dioxide is 0.309, so I have 0.309 divided by 44 times by 12. And that gives me a mass of 0.08427. Hydrogen is equal to 0.142 divided by 18 times 2, because there's 2 moles of hydrogen for every 1 mole of water, times the RAM of hydrogen, and I get 0.01578. And then I continue exactly the same way as before. I write out my little table. My RAM gives me my number of moles, divide through by the smallest, and I get 1 to 2.24. Remember, you can't round these numbers. You would have to times it up. So actually the empirical formula is C4H9. And the last example is done in exactly the same way. We have our mass of carbon, our mass of hydrogen. We take that away from the mass of the compound to give us the mass of the oxygen. Those numbers go into our table, divide through by the RAM, divide through by the smallest, and we get a 1:4:1 ratio. So again, the empirical formula comes out as CH. So we're now in the second section of these notes, and we're looking at using PV equals nRT. Now, it's an equation you need to learn. Sometimes they'll give it to you in the question, but not always. So you do need to know this equation, and that is the pressure times the volume is equal to the number of moles times the gas constant times the temperature. And the gas constant is always given to you in your data book, and that is 8.31. You do need to be very, very careful of units, and this is what usually trips students up, not converting to the correct units. So everything has to be in what we call SI units. So pressure is measured in pascals. The volume is the one that usually trips up people because it has to be measured in meters cubed. Temperature in Kelvin, number of moles is easy, that's just in moles, and the gas constant is joules per Kelvin per mole. The one most students have struggling with is the meters cubed value. What you need to think about is how you would convert a centimetre into a metre. So if I wanted to convert centimetres to metres, I would divide by 100. So 100 centimetres divided by 100, that's 1 metre. 120 centimetres divided by 100, that's 1.2 metres. Now, when I want to convert from centimetres cubed to metres cubed, I do exactly the same thing, but cube the value. So I'm dividing by 100 cubed. Now, when I do that, that's the same as timesing by 10 to the minus 6. Okay? So that's something that you need to remember. Again, some of this data is given to you in the data booklet, but if you can remember how to convert centimetres into metres by dividing by 100, centimetres cubed to metres cubed is dividing by 100 cubed, or timesing by 10 to the minus 6. So let's look at our first example. And we're going to write down our values down the side. So P, V, N, R, and T. And I'm going to write down the values that I've got. So I've got a pressure of 120 kilopascals. I've got a volume of 58.5 centimetres cubed. I don't know the number of moles, that's what I'm being asked to calculate. R is 8.31 joules K to the minus 1 mole to the minus 1, and the temperature is 70 degrees Celsius. Now what I need to do is I need to convert all of these into the correct units. So 120 kilopascals is 120 times 10 to the 3 pascals. 58.5 centimetres cubed is 58.5 times 10 to the minus 6 metres cubed. The R value stays the same, and the temperature changes. I'm going to add 273 to this to convert it into Kelvin, and I get 343 Kelvin. I've got my equation, PV equals nRT. I want to work out N, so I'm going to rearrange this to make N the subject, and it becomes PV divided by RT. Now I can put my numbers in. So P, 120 times 10 to the 3 times 58.5 times 10 to the minus 6, all divided by 8.31 times 343. And I get this answer equaling 0.00246 moles. Now I want to work out the molar mass. Well, I know the mass and I know the number of moles. Molar mass is grams per mole. So my molar mass equals 0.280 grams per mole, 0.00246, and I get 114 grams per mole. So we're looking at example 2 on the top of page 11, and we're going to go through the same procedure. We're going to write down P, V, N, R, T. Well, the pressure this time is 50,000 pascals. My volume is 0.06 meters cubed. N, again, is what I'm trying to figure out. R is 8.31 joules mole to the minus 1 K to the minus 1, and my temperature is 283 Kelvin. This time they've been nice to me because all the units are in SI units. So again, PV equals nRT. I'm rearranging it to make N the subject, so PV over RT. I'm going to put all these numbers in and press all the numbers on my calculator, and I get 1.28 moles. So that's my number of moles. So I'm doing the same thing in the next example, but this time it's the volume which is unknown. So I put all the rest of my numbers in. This time I'm rearranging this to make V the subject, so it becomes nRT divided by P. Put those numbers in my calculator and I come out with my meters cubed. Next one, I'm working out again an mass of neon gas this time. Again, I need to know the number of moles. So again, I put my values down, check that everything is in SI units, put it into my rearranged equation, and I get my number of moles. Moles times RAM will give me mass, so I should get 2.30 grams. And the same idea in the last example. Again, I'm writing out everything in the right SI units, so I've changed my pressure into pascals, and I've changed my volume into meters cubed. I've changed my temperature here into Kelvin. Everything is put into my equation, and I get my number of moles, and my RMM is going to be grams per mole. So it's mass divided by mole, and I get an RMM of 16.1 grams per mole. So that just finishes this section of the notes. In the last section, we're going to be looking at combining combustion analysis and PV equals nRT to find both the empirical and the molecular formula. We're then going to look at a little section at the end looking at percentage yield and atom economy. But until then, take care, stay safe, bye-bye.